Rule 1, if we know temperature and composition, T stands for temperature, CO for composition, then we know the number of types of phases present. For example, in this given binary phase diagram, as we can see, say for example for point A, where is point A? I don't see it here, down here. For point A down here, we know temperature, we know composition, so we know there is only one phase available, and it is solid. For point B, it is in the two-phase region. We know that there is liquid and solid at the same time, which do exist. That's rule number 1. Rule number 2, if we know temperature and composition, then it means that we know the composition of each phase. Meaning that, for example, in the two-phase region, right here, in the two-phase region right here, point B, in point B, we've got two phases present at the same time, solid and liquid, right? For the other two regions, it's easy, so I don't explain. If we are in point A, composition is exactly the same composition, which is down here, so 35% nickel. If it is in point B, again, composition is the same, because there is only one phase present. The challenging part is the two-phase region, which is in point B. At this point, we've got two phases present at the same time, solid and liquid. And we have different compositions for each phase. What is the composition of each phase? We've got to draw the tie line right at this point. Tie line, or making use of the lever rule. We've got to draw a horizontal line. From that, at that given point, we've got to draw a horizontal line, which is called the tie line. The intersection of the tie line with liquidus and the intersection of the same line with solidus tells us the composition of the two different phases. Okay? So for point B, the composition, what is the composition of the liquid phase? The composition of the liquid phase, we've got to bring it down, right here, find the intersection and bring it down. The composition of the liquid phase, which is Cl, composition of liquid, is 32%. The intersection of the tie line with solidus gives us the composition of the solid phase. C alpha stands for the solid phase, which is 43%. So the solid phase, the composition of the solid phase is 43% nickel, the composition of the liquid phase is 32%, but the overall composition of the material is, the whole material is 35%. The overall composition is 35%, or the average composition, I would say. Okay? So this is the way that tie line works. Rule number 3. If we know temperature and composition, then we know the amount of each phase in weight percent. Example. Again, I am not talking about points A and B because it's easy. Talking about point B, which is in the two-phase region. We've got to draw the tie line, and by making use of the lever rule, which is shown here, the weight percent, W stands for weight percent and L for liquid. The weight percent of liquid can be determined if we measure the length of the line from the given composition to the intersection of this line and solidus, and the length of this point from here to the intersection of this line and the liquidus. And we name each part by R and S, and then put the lengths of each line in this equation, just like that. In this equation, just like this, then we can easily compute the weight percent of liquid, and what is left is, of course, the other phase, which is the solid phase. How do we measure the length? If we project this point down, it gives us the composition, which is 43. If we bring this point down, it gives us the composition, and we know the composition of that one as well. So 43 minus 35 gives us the length of this bit of the line. 35 minus 32 gives us the length of this line, and 43 minus 32 gives us the total length of the line. Putting all these figures in the equation, we can easily compute the weight percent of each phase. Any questions on this? In the exam, I would ask you to bring a ruler with you to be able to measure the lengths and do the computations on the basis of that, on the basis of using your ruler. Yes? The composition is given to us. Look, point B. We are provided with the composition, which is 35%, and we are given with the temperature, which is whatever it is, say 1250.
That's given in the question?
It is given, yes. It is given in the equation. You are provided with composition, you are provided with temperature. So you can find the exact point in the phase diagram. And from that point, you've got to draw a horizontal line and find the intersection of this line with the two curves, solidus and liquidus. Then everything else as I just explained. Look, in the top it tells you, if we know temperature and composition, this should be given to you. You got that? Okay. Now this gives us weight percent. Say for example, if we know the weight of the material, which is for example 1 kilogram, then we can compute the exact weight of each of the phases. If the whole material is 1 kilogram, then at this given composition, 35% and 1250 degrees, what is the mass of the solid phase and the liquid phase then? 73% times 1 kilogram, which is 730 grams of liquid material, and also 270 grams of the other material. That's what we've got. Okay? So if the weight of the material or the mass is given, you can easily convert it to weight. Okay. And this is the Liouville rule, as I just mentioned. When composition is closer to liquidus, of course, we have more liquid. When it is closer to solidus, then of course we have more solid phase, depending on where it is. It's a tie line rule. If the length of one side is actually shorter than the other side, it means that there is more weight, because it has to balance. It has to balance, right? If it is shorter in one side and longer in the other side, there is more of this side compared to the other one in order to balance. It's the tie line, and like a teeter-totter, it works. Got that? This is what you already know if you have done materials and manufacturing 1 unit. Question. Who can answer this question? Is it possible to have a copper-nickel alloy that at equilibrium consists of an alpha phase of composition of 37 weight percent nickel, and also a liquid phase of composition 20 weight percent nickel? Is it possible to have such a composition? Yeah? Yes or no? Yes. Who says no? I say no, because it's not. Reason, if this is the case, we should be able to draw a horizontal line at any given temperature, giving us the given compositions. Let's see if it is possible. 37% nickel and 20% nickel for the liquid and solid does not give us a horizontal line. It's not a tie line. It's just like that, instead of being like this. Right? If we could draw a horizontal line, which one end of it has a composition, the intersection of this horizontal line gives us, with liquids, gives us 20% nickel, and the other end of it gives us 37% nickel, that would be possible. But right now, you can see that it's impossible. Yes? The statement of the problem is telling us, is it possible to have a copper-nickel alloy that at equilibrium, it consists of an alpha phase, which is solid phase, of composition 37%, which is this, it's solid phase, right? 37%, and the liquid phase of composition 20%, which is this. It means that we've got to be able to draw a horizontal line, which gives us a liquid phase of that concentration, a solid phase of this composition. It has to be a tie line for the same material. Okay? You can't do that. It becomes like this. You could have something 37 and say, for example, 27. We can have a composition of 37 and 27. But 20 is impossible. We got that? Because the horizontal line starting from here comes to this point, bring it down, it comes to about 27. Got that? Okay. Now, how are we going to do this problem? Determine the temperature of a 65 weight percent nickel, 35 weight percent copper alloy at which, look, composition is given. 65 weight percent nickel, you don't need to say with the rest, because what is left is the other element. There are only 12 elements in it. 65 weight percent nickel means what is left is copper. Alloy for which alpha, which is the solid phase, and liquid phases are present with the alpha phase of composition 78% nickel. Well, and then we've got to determine the composition of the liquid phase and determine the mass fraction of both phases. Are we able to do this? We should be. The composition is given, which is 65%, which is this one, right? Then the tie line, if we draw the tie line, this is what we get for that given composition. Okay? Temperature will be what is given here. So the composition is given. Then we've got to draw the tie line and find the temperature for which this composition is given, which is at 1340. Part B, determine the composition of the liquid phase. How do we do that? Of the liquid phase. This is what we just had, yes. Bring it down, gives you the composition of the liquid phase, which is that much. Determine the mass fraction of both phases. How do we do this? By making use of the Leber rule, which we just had. CO, O stands for overall composition, L stands for liquid phase, and alpha stands for the solid phase. So by making use of this Leber rule, we can compute the weight of the alpha phase, which is 0.55 or 55%. What is left, of course, is the other phase. That one is the solid phase, this one is the liquid phase. Okay? Good. Let's skip this. Okay, now let's do this problem. For a 40% of tin and 68% of lead, alloy at 150 degrees. Look, composition is given, temperature is also given. What are the phases present? What are the phases present for this given temperature and composition? 150 and composition is 40% thin. We've got 100% thin here. So 40% thin would be somewhere here. Temperature 150 somewhere here, right? So what we get, we've got to draw a line and find the intersecting point at this given point. And then what we will have, the phases that we will have is alpha plus beta, which is the answer. Solid, alpha solid plus beta solid. This is the two-phase region. Now, composition of the phases. We've got to draw the tie line again from this point to those Salvus lines on the two ends. The one to the left gives us the composition of the alpha phase, and the other one that of the beta phase. So again, at that given point, we do the tie line and find the projections, giving us 11% composition for 11% thin for alpha phase and 99% thin for the beta phase. And then the relative amount of each phase. By making use of the Weber rule, we can easily compute, which is 68% of alpha solid and also what is left of the other type of solid. Any questions on this? Okay. These are not yet the problems that we are supposed to do. We are just learning the things that we need to know in order to be able to do those problems. Okay. And then now for a 48% thin, temperature has now increased to 220. Where does it go then? It goes to the two-phase region of L plus alpha. How do we do this problem, this part? The phases present are alpha plus liquid. Okay. Again, we've got to do it similar to the one that we did before. We've got to do the tie line here, giving us the composition of the alpha phase and that of the liquid phase. The liquid phase, the composition of the liquid phase would be 46, and the solid phase 17%. Okay? And then the relevant amount of each. Again, by making use of the Weber rule, we can compute the weight of alpha phase and also the liquid phase. Exactly the same. It doesn't matter in which region of the phase diagram we are. Always we've got to make use of the tie line in order to find the compositions and also making use of the Weber rule in order to compute the weight of each phase.